Okay, so we're going to learn about thiols and sulfides, and I think you're going to find that much of what we've learned up to this point applies just exactly like you thought it would. Much of what we've learned, I got to get my pen just a moment, please. Much of what we've learned with respect to hydroxides and alcohols, right, will apply to sulfides and thiols. You notice that sulfur appears just under oxygen in the periodic table, so it's going to have very similar chemistry. Its valence shell looks very similar. It's a lot bigger, and so there's going to be some differences, right? It's got an extra shell in the core, right? So there's going to be some differences. The name of the compound is going to be pretty easy, I think, for you. And that is, let me get my pen here. The name of a butanol, right? And it's going to be similar, except we're going to put the syllable thi in there, and we're going to leave the e on there. Okay, so it's 3-methyl-1-butane thiol would be the similar compound, right? The analogous compound, I should say. All right, and then note that the e is not dropped. Okay, so thiols are also known as mercaptans, and we'll use that for some of the naming. Mercaptans. The sulfide group can also be named as part of a side group rather than as part of the parent chain. So, for example, in this compound, this is a butanol, but we've got the side group of which is we're going to call mercapto. All right, that is one of the least, I think, intuitive side groups that we've had up to this point. And you know what? I think it's going to require some getting used to. Okay, so the name mercaptan comes from their ability to complex mercury, so that's why it makes sense. Although, like when you're seeing something like that, right? The only reason we even discuss it is just to help you learn it better. It's not likely that's going to show up on a quiz or exam. So 2,3-dimercapto-1-propanol is used to treat mercury poisoning. 2,3-dimercapto-1-propanol. So let's go with it. Propanol. Here's 1-propanol, right? And oops, not 2,2. 2,3-dimercapto-1-propanol is used to treat mercury poisoning. Why? Okay, so I've already drawn its structure. All right, so thiols are known for their unpleasant odor. They smell bad. Skunks use thiols as a defense mechanism, natural gas, eggs. Your nose is a very sensitive instrument. This is I get these slides from Wiley, right? Kind of funny that they put those in here for us. Your nose is a very sensitive instrument, in case you need to be told that. So the hydrosulfide ion is a strong nucleophile. Look at this. Strong nucleophile and weak base. So before, we've oftentimes said nucleophiles and bases kind of track together, right? The ability of a nucleophile and a base sort of track together. Sometimes bulkiness matters, and that's the opposite of what's going on here. It's a strong nucleophile and a weak base, so we're going to expect it to do substitution reactions rather than elimination reactions. All right, so that said, predict the outcome for the following reactions and draw a complete mechanism. Please pause the video now and draw a mechanism and predict the products. Okay, so I'm going to suppose that you paused it. And so the hydrosulfide ion is going to look like that. Sodium's just a spectator ion, of course, right? So these electrons are going to come to the backside, boom, and that's going to go off here. Lost my head of my arrow there, and so we're going to get 1, 2, 3 propane thiol, 1 propane thiol. Okay, easy enough? Yeah, I mean, it's really simple when it's that small, right? All right, so let's do another one. Oops, sodium is the spectator ion. The hydrosulfide ion comes backside attack, boom. we get inversion of configuration, and so we get that. So what's the name of that? I'm going to let you name that without me. Pause the video here and name that. I'm not even going to tell you what it is. Okay? All right, so thiols have a pKa of 10.5, and that means that they are better acids than water, right? Because water is there, right? Better acids than water. So if methane thiol is exposed to hydroxide, this is going to go in equilibrium, right? And the better acid is going to donate the proton, right? So which is a better acid? Well, this has a pKa of about 11. This has a pKa of about 16, right? And so this reaction is going to predominate. The forward reaction is going to predominate, right? So it is a better acid. It's not a very good base. All right, so and thiolates are excellent nucleophiles, which we said before. Excellent nucleophiles. So we're expecting substitution reactions, SN1, SN2. Well, actually, excellent nucleophiles, right? Oftentimes, SN2. Agree? Okay. So a thiolate can attack bromine to produce disulfide. Okay, look at this. This is didn't translate properly. You know that's a sodium plus ion. That's a minus. Here's a sodium plus ion. That's a sulfide minus. That's a mistake, right? So here's how this happens. You've seen this before with alkenes. You saw something like this. So the lone pair of electrons here attacks this bromine, and this other bromide gets kicked off, right? And so then this other thiolate comes over and attacks that sulfur, and kicks off that bromide, right? And you get your disulfide, which you've seen this in biochemistry. Disulfide bridges are very important for cysteine interactions in proteins for secondary and tertiary structure. Tertiary structure, really, I think it's tertiary structure. For tertiary structure in biochemistry. So this is how this happens. Well, it doesn't happen with bromine, but you get disulfide bridge, right? Okay. So in order to how we're going to see this on a quiz or exam? Well, you've got these two thiols, right? It's 1, 2, so it's ethane thiol, right? Ethane thiol, we deprotonate it with hydroxide, which we saw in a previous slide. That's going to happen. And after we deprotonate it with hydroxide, then we have this, right? So, lost my note here. We deprotonate it with hydroxide, and then we've got two thiolates. They attack the bromine, and bam, we get a disulfide bridge. This is the whole mechanism that you need for this is right here, and I hope you'll know this, okay? So the next question is, how does the oxidation number change? How does the oxidation number change? All right, I'm not going to answer that for you. Okay, so disulfides can be reduced by the reverse reaction. So we'll do this with HCl and zinc. The interconversion between thiols and disulfides can also occur directly via free radical mechanism, and it'd be good for you to propose how that might happen. What kind of free radical? Give you a hint. Go back to your oxygen, right? Consider that, because oxygen and sulfur are right next to each other on the periodic table. We're right above and below each other on the periodic table, right? Propose a mechanism for that. Okay, so the bond dissociation energy of an SS disulfide, an SS bond, is only about 53 kilocalories per mole. And why is this significant? That's pretty low, isn't it? 53 kilocalories per mole. Why is this significant? I'm just dumping a lot of good questions on you here, aren't I? Okay. Sulfur analogs of ethers are called sulfides or thioethers. So we can, you see that? Look, we can name this very easily just by calling it a sulfide instead of an ether. Diethyl sulfide, diethyl ether, same thing. Well, not the same thing. You see what I'm talking about. Sulfides can also be named as a side group as methoxy. See methoxy or methyl thio group. Okay. Methoxy, methyl thio. It's not nearly as pretty as methoxy. We just got used to that. But I want you to see that methyl thio is just like methoxy. So if you get rid of oxy and put thio in there, and hopefully you're getting used to by this time of the conversation, or by this time of your homework, getting used to the when you say thio, you automatically think of sulfur. So maybe that'll help. Okay, sulfides are generally prepared by nucleophilic attack of thiolate on alkyl halide, which you would have predicted. Actually, we saw this before. This is one of the first reactions we did. This is how they're prepared. So you get your alkyl halide, and you take your thiolate ester, or rather your thiolate. No, thiolate ester. Sorry. Take your thiolate. So really, what you've got, right? You've got your thiol. Then you treat it with hydroxide. You treat it with hydroxide, it becomes RS minus, right? And that's what we've got here. Okay. Oops, I just answered that question for you. How are thiolates generally prepared? Sorry, I just answered it for you above. I'd forgotten that was coming. Okay, sulfides undergo a number of reactions. So first of all, you can attack on an alkyl halide. And the first reaction we're going to memorize is attack on an alkyl halide. Okay, no surprise there. That's like you see a lone pair of electrons. So you see essentially a nucleophile, right? The nucleophile, boom, and you get this monster here. The process produces a strong alkylating reagent that can add an alkyl group to a variety of nucleophiles. So now we can have, this is really an excellent leaving group, as you might not have surmised, or might not be surprised to find out. Excellent leaving group, because it was sort of neutral in the beginning, right? So nucleophile comes in, boom, alkylating agent. Okay? This is interesting. It's a really great way to add a methyl group to a nucleophile. Okay, you've done this kind of reaction a lot of times. So try to look back and think of what box you have in your head for a nucleophile coming in and getting an alkyl group, and you have a leaving group that leaves. What's the mechanism here, by the way? I don't have that written out here, but what is the mechanism? You've seen this mechanism over and over and over again. Name it. Say it out loud. Okay. All right, now sulfides can also be oxidized, and the way that they're oxidized, when they're oxidized, they go from a sulfide to a sulfoxide. Okay, and if they're oxidized even further, we see a sulfone. Okay, you've seen sulfoxide before, though. This is a common solvent in organic chemistry, and then the reagent that we do to get this reaction, there's a reaction for you. The reagent to get methylphenyl sulfoxide is sodium metaperiodate. Okay. Hydrogen peroxide can also be used to give the sulfone. Okay, so here's another reaction. Okay. Okay, so sulfoxides and sulfones have very little double bond character, surprisingly. So which resonance contributor, if they have very little double bond character, this question here is going to help you get this. If they have very little double bond character, which resonance contributor for each is the major contributor and why? Pause the video and point to one or say it out loud. If you've got your slides, then underline it or circle the one that's the major contributor and why. Okay? Look, this is the major contributor, and it's because they have very Can you see that? Because they have very little double bond characters. This is the major contributor, right? So what about this one over here? Which is the major contributor and why? Did you already say it? This is the major contributor, and it's because sulfoxides and sulfones have very little double bond character. What's the simplest sulfone? Does this look familiar to you? You ever seen this before? Okay, so it's a common moiety. It's a common functional group in sulfa drugs, for one thing. But it also looks kind of like sulfuric acid, doesn't it? Now, these aren't R groups. If these were really hydroxides, right, that would be sulfuric acid. Okay? So that's the major contributor because sulfoxides and sulfones have very little double bond character. Okay, now sulfides are readily oxidized. They make good reducing agents. So when we are doing ozonolysis, which we did ozonolysis in section 9.11, we take a double bond, we treat it with ozone, step 1, and step 2, we treat it with dimethyl sulfide, DMS, and boom, we cut that thing, right? All right. So we, first of all, oxidize the bejeebers out of this guy, right? See this double bond? We give it like a ton of new carbon-oxygen bonds, right? Well, specifically 4, I guess. Okay, and then we cut it. We oxidize the sulfur and reduce this guy. All right. So finally, this is our last slide. Predict any products or necessary reagents in the reaction sequence below. I think I'm gonna leave this for you. But you definitely have all that you need in the previous slides to answer this question. So be ready to talk about this in class. That's a lot of information, isn't it? Hopefully the vast majority of it maps over very nicely to what you learn about oxygen containing compounds, alcohols and ethers. Okay, good luck.